Okay, chapter 3, basic chemistry, Pearson. In this one, we will talk about classification of matter, states and properties of matter, temperature, energy. We will not talk very much about specific heat in detail. We will tell you what specific heat is, and that will be it for this, and energy and nutrition. If you take a look at the syllabus, it tells you the key things that we want to make sure you leave from these lectures, from these classes. All right? And we'll tell you at some point we'll tell you a little bit more about how to prep. But keep in mind, my slides are the study guide. All right, matter is anything that has mass and occupies space. Yes, you're matter, you matter. It makes up all things we use, such as water, food. These are just examples. Plastic bags. We can classify matter according to its composition, and we're going to talk about that and how we do that. For example, the human body is composed of carbon, hydrogen, and oxygen, a little bit of phosphorus, and some nitrogen thrown in there. Then there are a few other materials around for kicks and grins to make you function the way you function. But things have composition. And so when you think about matter, you really think about what's the composition. And when you think about that composition, how does that composition interact in nature, in life? Here we show you a diagram of matter, and we talk about pure substances and mixtures, and you will want to memorize this diagram. It will come back to see you over and over again. You have handouts that we're going to go through some examples of these after we go through the formal lecture. We'll have some work sessions that will go into the details. So the lecture here will not deep dive yet. We'll do that in the work session. Does everyone follow what we're doing today? That's how we're going to approach it, okay? But let's just take a look at it here. We have what? Pure substance, and we have mixtures. One way to know a pure substance, if it's on the periodic table, there's a periodic table here, and I suggest that you want to know where your periodic table is in your book, because we will, from now moving forward, refer to it a lot. We'll maybe try to print some for you so you have it handy all the time. So you will want to know where your periodic table is, because we will talk about it over and over again. I would teach these 2 chapters and the next to come a lot from saying, look at the periodic table, and this periodic table shown here in the room. So if it's on the periodic table, it's a pure substance. So that's it. So if you look on the exam, you will always have a periodic table there. Okay? So if you see an example, if you see Fe, look on the periodic table. Yep, it's there. Okay, pure substance. Carbon dioxide, where there's carbon and there's oxygen. Yep, pure substance. You get it? If you can see it on the periodic table, it's going to be a pure substance, because we have elements on the periodic table and we have compounds on the periodic table. Compounds are composed of elements from the periodic table. That's it. That's straightforward. So if you make a compound, then it's going to be from these elements on the periodic table. And before the end of this course, you will know how to put those together to make several types of compounds. So we have elements and compounds, again, from the periodic table. Here is the element. Here's a compound of water, composition of 2 moles of oxygen, 2 moles of hydrogen, and 1 mole of oxygen. Then we have mixtures. Now mixtures we have these elements and these compounds, and we've made them into wonderful things. For example, brass is a combination of copper and zinc, and it's a homogeneous mixture, meaning that you can't easily take it apart. If you look at brass, you cannot see copper, neither can you see zinc. You see brass. Okay? Okay? Does everyone follow? So that means it is a homogeneous. Paint is a combination of organic materials and some other things thrown in there and many additives. You can't see them. All you see at the end of it is paint. But you actually know that the can of paint, most people paint, know it's heterogeneous, right? That's why you shake it. So here's one way to know. If you have to shake it, it's probably heterogeneous, like salad oil. Paint in a can is heterogeneous, but once you put it on the wall and it cures in, it becomes homogeneous coating. So it's a homogeneous coating, but it's a heterogeneous mixture. Does everyone follow? So where you talk about it is very important. Okay? So we have homogeneous and we have heterogeneous. So if you could take microscopic tweezers, you could go in and pull them out, then it's heterogeneous. Does everyone follow that? Okay? An example of a homogeneous mixture is iced tea. Sweet tea is homogeneous unless you're down south. If you're down south, it's liquid, man, it's liquid syrup. I'm telling you what, the sugar is sitting on the bottom of the glass when you go down south.
Sitting on the table right there for you to put more in.
Oh yeah, put more in. That's right.
My brother-in-law's from Virginia, so we go down there. That's yeah.
Listen, it's heterogeneous. Okay, I don't care what they tell me. It's heterogeneous when you drink. Okay, you get it? So that's what matters. You get it? So you can pass that point to where it's homogeneous, to where it's supersaturated. Supersaturated then becomes a heterogeneous. You get it? And that's how we think about it. All right, and by the way, again, you now know yes, I do not have an indoor voice. I just don't. Okay, a pure substance classifies type of matter with a fine, fixed, and definite composition. It's definite. That's it. That's what it is. It doesn't change. Brass is brass. Steel is steel. You get it? All right? Diamond is diamond. Okay? Cubic zirconia is cubic zirconia. An element is composed of just one atom. It's just that. That's all it is. And a compound is composed of many. That's what we just showed you. We expect you to know these definitions. If it's in bold and it's a definition, we expect you to know them. I tend not to ask many definitions on the quizzes, so you might expect, on the exams, definitions. So you want to bone up on your definitions for the exams. Elements are pure substances that contain only one type of material. That's it. Okay? If it's on the periodic table, that's the easiest way to know it. Just look at the periodic table. And that'll tell you it's an element. If it's not on the periodic table or it's composed of two materials, it's a compound. Two materials from the periodic table, compound. Single material from the periodic table, element. You got it? So simply look at the periodic table. Do not try to memorize all the elements of the world. I will tell you the elements and the compounds that I expect you to know at the end of this course. For example, by now you should know water, right? Yeah. And you should know carbon dioxide because I've talked about it a lot. You get it? Okay. Compounds exist with two or more elements in a definite ratio. Okay? That ratio is fixed. This is sodium chloride. This is table salt. That's what it is. This is table sugar. Okay? This is what it is. It's not something else. It's not something close to that. It is that. It's very definite. Water is H2O. H2O2 is hydrogen peroxide. That's not water. O2 is oxygen. O3 is ozone. It's exactly what it is. Okay? Keep that in mind. I think you intuitively know that, but we want to make sure we emphasize it. Table salt is a compound that contains elements of sodium and chloride. If you look at your periodic table, you'll see sodium's on the left side of the periodic table and chloride's on the right side of the periodic table, and we may move that periodic table when we do this the next time. If you look at it, it's on the far left. Salts, make a note of this, salts are generally formed from elements on the far left with those on the far right. That's a salt. That's going to come back to haunt you in this class. If it's an element on the far left of the periodic table with an element on the far right of the periodic table, it's a salt. When we talk about the periodic table, and you'll learn more about that, when we talk about compounds bonding, we do not count the last row, 18. Got it? That's noble. The noble gases sit around and do nothing except be noble. Get it? So when we make a salt, if you see it from the far left and the far right, it's a salt. So everyone follow. That's important to note because that's some things you're learning, and you'll see this come back to haunt you. So that's how we make salt, and that's why I have sodium chloride. So if we can make sodium chloride, wow, we can make something that's a little better for your blood pressure with cesium chloride because it's far left and far right on the periodic table. Mixture, you know what a mixture is now, right? This type of matter consists of two or more substances that are mixed, but not chemically combined. There's no chemistry there, okay? The chemistry of paints occurs after you put it on the wall. While it's in a can, there's no chemistry. They're just molecules sitting around the paint can. You put it on the wall, it cures. Cures means chemistry took place, okay? When you make your bread at home, initially, when you make up the dough and you make the mixture and you knead it and all those kinds of things, that's a mixture initially. And when you put it in the oven, chemistry takes place called baking. Okay? So you can take a mixture and you can transform it into something that's not a mixture. That's really, you get it? Okay? Becomes homogeneous cake if you can bake well. All right? So here, homogeneous. Again, here is homogeneous, here heterogeneous. If it's homogeneous, you can't easily separate it. Does everyone follow? Okay? All right? heterogeneous, we can easily separate it into its parts. Any questions so far? We're all good? Pace is okay? Okay, states of matter. In this course, we will only talk about 3 states of matter. In some courses, you will talk about 5. So we limit our discussion in this course to only 3. That's solid, liquid, gas. You get it? There it is. That's it. Solids have definite shape, definite volume. Closed particles, and you need to know this definition. If it's closed particles, it's a solid, and that's what makes it more dense. The particles simply sitting there, they're vibrating. The wall's vibrating. You just can't see it vibrating. But they're vibrating very, very slowly. So slowly you can't really see it. Okay, there's not much motion in it. All right? Strong attraction, a very strong attraction, and that's why they're solid, and that's why they densify. Liquids have definite volume, but not a definite shape. It takes on the shape of whatever container you put it in. You know that. My coffee takes on the shape of this coffee mug. Your water takes on the shape of that particular container. Gases will fill the entire room, right? And there is a problem with getting in the elevator with people after having Taco Bell. It will fill the entire elevator, okay? It's a gas. That's what gases do. You get it? It doesn't stay put, okay? So you'll want to know these definitions and be able to differentiate a solid, a liquid, and a gas. Evaporation. Let's talk about one of the things, a very important principle that happens to liquids. Okay? Liquids can evaporate. And evaporation occurs when water molecules gain sufficient energy to escape the liquid phase and enter the gas phase. So what happens with water? You have it sitting around, right? And it's sitting there and the temperature increases and it evaporates. You know this. But the reason it happens is because those molecules in the water phase, they have these strong attractions, and as the temperature rises, they start to lose those attractions, and it's trying to get into the gas phase. In general, it will prefer to be in the gas phase because of a term called entropy disorder. It would prefer to be more molecules spaced further apart than lots of molecules put together. Sounds like a bunch of people, right? Okay, you get it? I want my space. Please get out of my space. That's just what that. So these molecules are heated up, and once that vapor pressure reaches that, okay, at 100 degrees C, it goes into the gas phase. That's called evaporation. We call it the boiling point. The energy overcomes the attractive forces and goes into gas phase, and each liquid has a different boiling point. They're not the same. Nail polish remover has a different vapor pressure, a different boiling point than water, and it's lower than water in its boiling point, but higher in its vapor pressure. The general rule of thumb is vapor pressure and boiling points are opposite. If it has a high vapor pressure, it has a low boiling point. If it has a high boiling point, it has a low vapor pressure. You'll want to make notes of that. So these are properties of liquids in terms of evaporation. The other thing a liquid can do is a liquid can condense. Condensation, water vapor is converted to liquid. That's what happens when you're making your meals on the stove, right? You boil it up and the water keeps boiling and it keeps hitting the lid and it keeps dropping on the stove. That's called condensation, but as soon as it hits the stove, it's hot and it goes right back into the gas phase. Okay? So you have your liquid, goes to gas, refluxes off of your container, off your lid on your stove, hits the stove as a condensed liquid, goes back into the gas phase. So this goes over and over again. Condensation simply means it's leaving the gas phase back to the liquid phase.
Before you move on, can you say that again? The high boiling point has a low what pressure?
Yes. Vapor pressure.
Vapor pressure, thank you.
So high boiling point means low vapor pressure. High boiling point means low vapor pressure, means that it does not want to go into the vapor phase. High vapor pressure, low boiling point means it wants to go into the vapor phase. That's what it would like to do. Okay?
Okay, move on. Thank you.
Here we go. Ready? Then we have a process we call sublimation. where we go simply from the particles the particles on the surface of the solid change directly to gas with no temperature change without going through the liquid phase. This is what happens at Beyonce's concert. Okay, Tim McGraw's concert. Okay, Toby Keith, whoever you like. Okay, all right. When they have the drives, the smoke on stage, the solid is subliming. That's what happens when you CO2, carbon dioxide. It simply goes from the solid phase. It bypasses the liquid phase. It's actually it's on a diagram, an energy diagram, where it actually doesn't bypass it. It actually doesn't see it at all. But we say, for teaching purposes, it bypasses it. But it goes from the solid directly to the gas phase. That's it. That's called sublimation, and you will want to know all of these definitions. Okay? And so this is what happens. For example, dry ice. Carbon dioxide sublimes at minus 78 degrees. It's called dry because it does not form a liquid as it warms. When it warms, you don't get a puddle. You don't get a puddle. Okay? All right? In extremely cold areas, snow does not melt, but sublimes directly to vapor. Okay? And that's important to know. All right? So it just doesn't go through the liquid, doesn't melt to the liquid. It just goes from snow to vapor, makes clouds, and eventually comes back. Got it? These are important things to know about matter. So, here's a summary of the three states that we will talk about. Again, we will only talk about three states in this class. Okay? Solid, liquid, and gas. You do well to know this table. All right? It shows the key information that we'd expect you to be familiar with in terms of talking about this. Okay? This is the type of information that you talk about when you go to parties and family reunions and things of that nature. You know, you get together, hang out. Yeah, you kind of talk about this kind of information. You know, you start talking about the arrangement of particles when it comes to solid, liquid, and gases. Yeah, that's the way you do it.
I was just talking about that at work last night.
I see. Physical properties. All right, let's talk about physical properties. Physical, that's the key word. Physical properties. Characteristics observed or measured without changing the identity of the substance. You don't change it. Water is wet. Okay, the world around, water is wet. You get it? Okay? Shape, physical state, boiling, freezing, points, densities, colors. These are all part of their physical properties. This is what makes it what it is. Okay? This is its identity. For example, a penny is round, has an orange-red color, and has a shiny luster. That's just what it is. You get it? So when we talk about physical properties, it is what it is. So everyone follow. That's its physical property. Okay? It's rectangular. Physical properties occur when matter undergoes a physical change of state, but its composition remains constant. This is what happens here when water exists in the three states: ice, water, and steam. So we have the ice, we have the water, we have the steam, which you're familiar with. These are all physical. It's solid, it's a liquid, it's a gas. Those are physical states of water. Chemical, on the other hand, describes the ability of the substance to interact with other substances, to change into a new substance. Cooking sugar at high temperatures changes the chemical properties. Leaves browning in the fall turn green in the summer. This is all chemistry. Okay? By the way, dyeing your hair is not chemistry, it's physical. It's like coloring. Crayons. Okay, keep that in mind. That's a tricky one. I always ask that one. That's a physical change. It looks like chemistry, but it's really just physical. It's just a physical change. It's like painting a wall. Okay? The paint drying is chemistry. Okay? what the paint did to the wall was a physical change. Does everyone understand how we think about it and how we talk about it? Okay, so you have to think about it. What's it doing? Not just memorize this list of them. Okay? All right? All right? So, you want to keep that in mind. But one way, if you cook it, it's always chemistry. For example, toast in the toaster is chemistry. Toast in the microwave, unless you're really bad, is physical. There's no chemistry that occurs toast in the microwave. In a microwave, water molecules start to spin and rotate. And they rotate so fast that they form friction. That friction forms heat. That heat is transferred to the bread. That's no chemistry. In the toaster, you actually brown the carbon units. Okay? Chemical change takes place when an original substance is converted to a new substance with different physical and chemical properties. For example, iron nails corrode, okay, in the presence of water. A new substance form is red. Powder called iron oxide. It's rust. Okay? And in this case, it's iron 3. So, physical and chemical chain properties. Here it is. You do well to memorize these definitions. This is a summary of it all. The way I'll be asking you, I don't think I ever really ask the definition of these. I give you examples and expect you to use it in this case. We're all good? Let's talk about temperature. This is important. Temperature is a measure of how hot or cold an object compared to another object is. Okay? That is not the same as heat. Temperature and heat are not the same. Keep that in mind. That's a pet peeve of mine too. It's one of those things that I like for people to know. Okay. Temperature, okay, measures the average kinetic energy of a substance. So what's the average kinetic energy? That's the temperature. And that's read with a meter. Heat is the flow of energy, okay, from a warm body to a cold body. That's why you feel cold when you go outside. The cold air doesn't cool you down. You're actually your body's trying to warm the outside up. So your heat is leaving you and is going to the outside. You're actually trying to warm the entire outside.
How stupid is that?
That's what your body wants to do.
I want that heat.
That's correct. You get it? But that's exactly what it wants to do. It can't help itself. That is the nature of the physics. As soon as heat flows from a warm body to a cold body, that's heat. So each time you go into a cold area, you're going to get the chills because it's going to happen. Okay? That's how it works. Always. Okay? Grandma says, close the door. You're letting the cold air in. No, Grandma, I'm letting all the hot air out. You get it? It's a flow of hot, warm to cold. Okay? But temperature measures, okay, the average kinetic energy, hot and cold bodies. Okay? It's measured using a thermometer. We use Celsius in science. Celsius and K is what we use in science. For the most part, you will use Celsius. Okay? Although I don't know in hospitals they use Fahrenheit, I don't remember. These Fahrenheit, these both, because people are so familiar with Fahrenheit. So you'll want to be familiar with both, right? It's Fahrenheit and Celsius. And here's the scale. We have a Fahrenheit, Celsius, and Kelvin scale, and this just shows the conversion. And we're going to practice doing the conversions. Okay, we're going to show you here. Well, all of these things we've talked about here, we're going to go through practice sheets to do them all. Okay, today's math session. We'll always have a session like that where we practice doing what we talk about. Okay, so let's move on and we'll practice it. We're going to practice doing this conversion. Okay, so be familiar with it. This is what it looks like. this is how we convert between degrees C and Fahrenheit. So we want to go from Fahrenheit. And here's the and convert Fahrenheit. So this is Fahrenheit from C, and this is convert Fahrenheit to C. Okay, and this is how we do it. We will practice this in a minute. Body temperature. Body temperature is about 41 degrees C. It's actually a little less. Okay. It's about 41 degrees C. Just as a note, okay. As a note, you can always tell when something's hot. If you feel it warm, that means it's above 41 degrees C. Typically, you'll hear people like me say above 40. Okay. All right, so be aware of that. So if you get touching and feel warm, you're above 40. That's how you'll know. Okay, that's how moms know that the kid's sick. They feel it, and that temperature is above your register. Okay. Because you're at 41, and they're 41.5. Get it? And you feel that difference. Okay.
I have a question.
Yeah.
So thinking about that and the temperature, the heat moving from hot to cold, is that why, like, long time ago when kids would have fevers, like in the 1800s, they'd put them in ice to try to draw the heat out?
That's exactly what they were doing. Her question was, in the early times, they would put them in ice. Yeah, they're trying to cool, they're basically cooling them down. And the heat is going to flow from the warm body to the cold body. That's exactly why they were doing it. Yes, they were icing them down. That's exactly right. Okay, but in doing that, it would draw the temperature down. But what was causing the temperature was not addressed. What infection, what's happening in the metabolic process. But that's exactly right. That's what they were trying to do. Good question. So here we have body temperature above 41 is called hyper, above. Typically hyper is going to be above, hypo is going to be below. Okay? All right? Hyper, heat or temperature. Hypo, heat or temperature. That's what we have here. You'll want to know these terms. All right? Ice bath is what we're talking about. Okay? It's the flow. All right? Heat flows from a warm body to a cold body. And so here, well, you want to stay above a certain amount. Why? Your machine, your operating device, your operating system, you can't operate below a certain temperature efficiently. Okay? And so your body goes into shock. It says shut down or reboot, but it often won't reboot. It just shuts down. But it's actually just trying to reboot it. It's trying to warn you, I need to reboot, I need to reboot, I need to reboot. Okay? So this is what's happening. That brings around the energy. Energy defines the ability to do work. Energy is work is movement against a force. Work is force time distance. So the further you go, right, with that force, the more work you do. Intuitive, isn't it? But these are the formulas we use. So energy is defined as the ability to do work. That's energy. If it does work, that's energy. Okay? Two forms of energy that we talk about, kinetic and potential energy. Kinetic is energy in motion. If it's moving, it's kinetic energy. If it's standing still, it's potential energy. If it's a composition, it's potential energy. For example, a Snickers bar has more potential energy than perhaps some other M&Ms or something. You get it? Potential energy. How much energy is there? Potential energy has to do with based on the position or the composition. So let's talk about the composition first. So that's why there's certain foods you eat, because you say that's going to give me more energy because it has more potential energy in there. That apple has potential energy, banana has potential energy, the grapes have potential energy. Yeah, and even the Snickers bars and the bean burritos from Taco Bell, they all have potential energy. That means it's there to be available if used. You got it? Also, position of potential energy means where it's located. For example, this cup at this position has more potential energy on the table than it does on the floor. The higher we are from gravity, the more potential energy we have. Note that. Okay. So an object sitting on top of the building has more potential energy than an object near the ground. And you intuitively know that, right? For example, if you drop a hammer, if you're standing on the ground and you drop the hammer to me, standing next to me, just above my head, I can catch it pretty easily, right? What happens when you drop from up top? You kind of know to do this, right? When you try to catch it, because you know it's coming, because of this equation. You get it? It has more potential energy because of its position. So the higher up, the more potential energy. The different compositions have different potential energy, and you want to be aware of that. This is why we eat certain foods. This is why, okay, the doctors prescribe certain things because of potential energy in that substance. Okay? You guys okay? Need a little bit, if you need to stretch, just stand up. Okay, we're going to keep pushing a little bit here, okay? Heat is associated with the motion of particles. That's what we were just talking about, right? That's the average kinetic energy in the particles. The faster particles move, the greater the thermal energy of the substance. And that's what happens in the microwave. The microwave causes the water molecules to rotate and rotate and rotate, and you're going to learn that that's not a harmful thing, and it doesn't leave bad things in your toast or in your bread or in the food you put in the microwave. There's a conspiracy. That is a conspiracy theory. Yeah, you will hear that some more. Okay? All right? So here, we talk about energy in terms of joules. Okay? All right? A heartbeat's about a joule. Punching your calculator is about a joule. Quick text message is about 3 joules. A really angry breakup text message is about 5 or 6 joules. Okay? All right? You get it? Okay. There's more energy in joules in an angry breakup text message in your kid breaking their knee or breaking their leg. Kid broke a leg, oh, that's okay, they'll be okay. Breakup, oh, that's really a lot of energy. You get it? So you're using each time. So each time you turn that book, you just use about a joule of energy. Okay? You write something with your pencil, you chew some gum, you rub about a joule. That's what you're using. Blink, okay, maybe a half joule will give you. You get it? That's energy. So that's what you're using each time you do something. You rub your hair, you scratch your head, about a joule. You get it? These are energies. Look what happens, and why do we keep emphasizing that? So now you understand how much energy is put in there to shock you back with a defib? That's a lot of energy, right? And that's what it requires. You're rebooting, you're telling that system, re-go. Okay? Takes a lot of energy, 360 joules. So when you be able to compare those. So you kind of have an idea here. It's a joule. Okay? Let's say a joule. Yeah. K-joule. Yeah. I think I'm right. Yeah, 1 joule. Yeah. And so here, 360 joules. Okay? I should have a chart on this. I bet you I do. Yeah. Here we go. Yeah. See? Pick an apple up. Yep. About a joule. Okay? Which is the same as rate. So every time you pick your calculator, about a joule. And here, this shows you how much energy was released at Hiroshima when the atom bomb. So long, you get it now, right? And so you see where your defib is somewhere in here. This is what it takes to kind of shock you back, give you an idea. I don't expect you to know all these, but I do kind of expect you to have a general idea. You know, I'll ask a question like you send a text message, you say a joule, that's the answer. If you say 3, that's fine. You get it? Just a small number. Okay, well, joules to do that. And I expect you to at least have an idea about a defibrillator, about 360. If you said 350, above 300, I'm probably going to be okay. Okay, this is an exact number here. Okay, but you'll look on the chart. It'll probably be something like a true false or multiple choice in this case, and you know the difference. Okay, but we like you to have an understanding of how much energy it takes. And so that's the purpose of this table, is just give you an idea. It's got an energy of a light bulb. Okay, and then we have the energy here of molecules. Okay. Now, energy, we don't expect it. This is a power plant, and I just like to show you this. This is how we produce electricity. I show you this because of this law of thermodynamics. This law you must memorize. Energy is neither created nor destroyed, but may be transformed from one form to another. That's it. You can't create energy, you can't destroy it. Okay? It's eternal. That's it. It's fixed. It goes on and on and on and on. What you have is what you have. It gets transformed. You take wood, you take a tree, you burn it, you convert it to another form of energy. Get it? Okay. You can't create it, you can't destroy it. but you can transform it. And so here I like to show you the common ways we transform energy to do things in life. We take potential energy, which is composition, in this case the fuel molecules here in this plant. Right? Fuel molecules have potential energy. Each time you fill your tank, so think of that, each time you fill your tank, you're putting potential energy in the tank. Right? Maybe I'll use that as the next example. Then kinetic energy is this. Once you fire the pistons, you start to create kinetic energy. Right? Move energy of motion. That energy of motion goes to the pistons and creates work in the piston. And this starts your cars are going, and then you turn on the radio and you drive off, man, and you really gun it. Okay? I drive a truck. Okay, that's it. I'm thinking of getting a larger truck. The only reason I have a larger truck, my wife refuses. She refuses to get in. I said, that'll work. No, just kidding. I have to erase that part, right? No. She said, I won't ride with you if you get a truck that big. I said, you won't? No. So anyway, my point here is this is all energy. You get it? It's energy, and it's transformed from potential to kinetic to mechanical to electrical in a power plant, and the same thing in your vehicle. Okay? So we take these two forms here, potential and kinetic, and we do something with it. Okay? Heat units, we'll talk about that, but here they are. You have to memorize these. We'll practice them when we do our math sessions. The unit, calories, is the amount of energy needed to raise the temperature of 1 gram of water 1 degree C. I don't need you to know that definition. I need you to be familiar with it, but what I really need you to know is this, that these number of joules equal 1 calorie. And this is a scientific calorie. Okay? This is an exact number. Remember we talk about exact numbers? This is exactly 1. You get it? It's exact. This is what it is. Okay? This then, if we have this equals this, can we use it as a conversion factor? Yes. Anytime you see something equals something, you can draw one above the line or below the line. You get it? Anytime you have an equal sign, it's a conversion factor. Okay? So we have a conversion factor if we play with energy here now, don't we? And you know how to use it, right? You take your given, times, draw the bars, and eliminate until you get your answer. This is important to note. Scientific calories, shown here 1 kilocalorie, and it's 1,000 calories, is 1 calorie for dietitians. So your 1 dietary calorie is actually 1,000 scientific calories. Okay? Therefore, we can do this type of conversion too, can't we? Right? So when you say, boy, I just burned 300 calories, right? You know you burned 300,000 scientific calories. And you want to know how many joules that is, you can do the conversion. Follow? And that tells you just how much scientific energy you used that day. So everyone follow that. Okay? All right? Let's keep pressing. We will work and do all of these. Carbohydrates are the body's primary source of energy. Snickers bars. However, when carbohydrates reserve exhaust fats, and then proteins are used for energy. So when the carbs are gone, we use the fats. So you want to burn. So when carbs are not there, the fats will start to burn. So you hear people say a low-carb diet. I'm on a low-carb diet. They're pushing to make sure this kicks in early. Because otherwise it's going to burn. It's going to just play with the carbs. It's going to leave the fat sit there. Okay? So the low-carb diet allows the fats to kick in. Okay? To use for the energy. Okay? So basically your body is burning material. You're a power plant. And you're burning material. And the thing that has potential energy is the carbon source. The carbs, the fats, the proteins. Okay? So the carbs, fats, and proteins are the primary source. These all have potential energy. This potential energy is converted into the fuel for your body. Here, scientific again. Notation for these. We say equal sign, therefore these can be what? Conversion factors. They always are when you see equal sign. Hang in there. Energy values for 3 food types are given here. We just want to show you the difference in the energy here, right? So this is just FYI. Okay, not sure yet how I'm going to test you on this part here or not. So just kind of stare at this table a lot, be familiar with it. Okay, you can see here we have the carbs, the fats have the higher number for us, right? Okay. Carbs and proteins are about the same. And that's what they've been showing you on the package. One of the things you want to note on these labels is the added sugar. That's usually the dietary problem, is the added sugar. Things have natural sugar. That's the way it is. You cannot avoid it. Okay? It's the added sugar. And the added sugar there is, yep, for that kick that we enjoy. It does, and by the way, sugar does not make the children hyper at night. That is a myth. Okay? So giving them sugar at night will not make them hyper all night. Now, they might stay up because they want some more sugar just because they like the taste of it and they enjoy it. Maybe that's why they get excited, but it in itself does not make them hyper. On the other hand, chocolate with caffeine in it just might do the trick. So be aware, these are food labels. I like to be familiar with these. The bottom line, I'd like for you to know what's listed on these food labels, the carbs, the fats, the proteins, and servings. And if it's per serving, that is a what now? Conversion factor. We can use that to determine. And by the way, I don't know who created these serving portions, but there's no way you're talking about 3 crackers is a serving. Are you nuts?
They wouldn't get you to buy it if they didn't put small servings on there.
Yeah, well, this is something.
You look at the amount of added sugar, the amount of saturated fat or added sugar, and then you don't see the serving size until you get home.
Oh, okay, there you go. I know there's something going on there, but
I'm sure that's what it is.
Oh, I don't know what it is, but I'll tell you, I don't agree with it. Okay, you get it? But we can use it for a conversion factor, whether we believe it or not, right? Okay, and whether we agree with why they did it. And we don't, okay, you get it? There's a lot of lobbying that goes into this. All right, the amount of energy needed by a human every day, this is important. Take-home message here is that anatomical females and males tend to need different amounts. That is the bottom line that I need you to take home from this. Okay? Anatomical females and anatomical males tend to need different amounts, and they need different amounts depending on their age. Now, what they didn't show you on this particular chart, if it goes to the when it goes to the seniors, it goes back to less actually. It goes back to somewhere less than this number here, so it kind of goes down. Okay, when it goes to seniors. Okay, it's pretty interesting. Okay, all right. So I need you to be familiar with that. Person loses weight when his or her intake of calories is less than the calorie he or she uses. You know that, don't you? Okay? So you take it a little less, you can lose weight. All right? Burns, walking, 200 calories. These are kilocalories. Okay? All right? So you have to convert those. And swimming, 500, and running, 750. There you go. You survived Chapter 3.